All right, let's talk about the symmetry of graphs. There's three types of symmetry we'll be discussing. So we have x-axis symmetry, y-axis symmetry, and what we call origin symmetry. So the first, x-axis symmetry. What that means is that if I fold this graph along the x-axis, so I just take this bottom part, fold it up across the x-axis, this will match exactly with that part. Y-axis symmetry means that I will fold along the y-axis, fold this part over here, and it'll match up exactly with that. Origin symmetry is a combination of those two, and we'll talk more about it in a minute. All right, so let's talk about some points on the graph. So say, for instance, that I had the point, let's say this is 1, 3. Okay, so the point 1, 3 is on my graph. If this graph has symmetry across the x-axis, then if the point 1, 3 is on the graph, the point 1, negative 3 also has to be on the graph. Another example, say the point 5, 7 was on the graph, then the point 5, negative 7 would have to be on the graph. Okay. In general, let me get rid of that so we have some room. So in general, anytime the point xy is on the graph of an x-axis symmetrical equation or graph, anytime the point xy is on the graph, the point x negative y also has to be on the graph. Let's think about a y-axis symmetrical graph. Okay, let's suppose that the point 5, 8 is on the graph. Then the point negative 5, 8 has to be on the graph. Or another example, let's say that the point 1, negative 3 is on the graph. Then the point negative 1, negative 3 has to be on the graph. Okay, so in general, anytime the point xy is on the graph of a y-axis symmetrical equation, the point negative x, y has to be on the graph. Okay, let's talk about a graph that's symmetrical with respect to the origin. Now, it's kind of a combination of these two. So let's imagine that I reflected this part of the graph up here across the x-axis. So if I did that, it would look something like this. Then if I reflect this blue part across the y-axis, it'll match up exactly with that. Imagine now we took the other part of the graph, so say this chunk, we flip it across the x-axis, it would look something like this. And then if we reflect that across the y-axis, we would get this part. So, to be symmetric with respect to the origin, you combine x-axis symmetry and y-axis symmetry. So I take this graph, reflect it across the x-axis, then reflect it across the y-axis, and I should get the exact same copy back. Okay, so let's think about points on that graph. So imagine that, let's use this example. Say the point 1, 2 is on the graph. If I reflect that across the x-axis, then you would have the point 1, negative 2. Then if I reflect that point across the y-axis, you would have the point negative 1, negative 2. So, if the point 1, 2 is on the graph, then the point negative 1, negative 2 will be on the graph of an equation with symmetry with respect to the origin. And it's a lot of words. So in general, anytime the point xy is on the graph of an equation with origin symmetry, anytime xy is on such a graph, the point negative x, negative y will be on that graph. All right, let's consider this equation, x equals y squared. Maybe let's make a graph of it. So in order to make a graph, let's plot some points, see what happens. Okay, so let's put in, let's say we put in a 1 for our x. If we put in a 1 for the x, what could y be? Well, y could be 1, because 1 squared is 1. But y could also be negative 1, because negative 1 squared is 1. Let's try a 4. Okay, so if I put a 4 in for x, what could y be? Y could be 2, because 2 squared is 4. But y could also be negative 2, because negative 2 squared is also 4. Let's try 9 for my x. So if x is 9, what could y be? Well, it could be 3, because 3 squared is 9, or it could be negative 3, because negative 3 squared is 9. So I get 2 points. Okay, let's plot those. So I've got the point 1, 1. I've also got the point 1, negative 1. I've got the point 4, 2. I've also got the point 4, negative 2. I've got the point 9, 3. I've also got the point 9, negative 3. What about 0, 0? That's also a solution, right? 0 is equal to 0 squared. So let's plot that one. And that will make a graph that looks like this, a sideways parabola. Reviewing from a few days ago, is this a function? No, not a function. It fails the vertical line test. So is it symmetric? It's symmetrical around the x-axis, because if I folded this over, it would match up exactly. The point 4, 2 is on the graph. The point 4, negative 2 is on the graph. So we think this is symmetrical based on those examples. We think it's symmetric with respect to the x-axis. Over here, we're going to prove for sure that that's the case. In order to prove it, we need to take an arbitrary point on the graph. So we need to take just some point xy. And we need to prove that the point x, negative y, is on the graph. And it sure looks like it is, and it kind of makes sense. So let's prove that. All right, so let's see if we can try to demonstrate that this is the case. All right, so we're going to say that the point xy is just some point on this graph. It can be anywhere on there. Okay, so our goal will be to prove that x, negative y, also is on the graph somewhere. So if it's on the graph, it has to satisfy this equation. So we have to be able to plug this point into this equation and it be true. So let's do that. If I put x negative y into this equation, what do we get? Well, so if I put x in for x, I'll just get x. If I put negative y in for y, I'll get negative y squared. Then I'll have x equals, well, what is negative y squared? Negative y times negative y is y squared. So that's true. So that means that this point, x negative y, also has to be on the graph. xy was on there because we put it on there. And then this equation implies that x negative y also has to be on the graph. So we've proved that this equation is symmetric with respect to the x-axis. Okay, so we've graphed y equals x squared several times now. We know exactly what that looks like, a parabola. So let's think of a point that's on this parabola. So we have 3, 9. It's definitely on there. Because if I plug 3 in for x, 3 squared is 9. Okay, to make sure that this equation, or this graph, is symmetric with respect to the y-axis, so this is y-axis symmetry. Sure looks like it is. To make sure that it is, we have to prove that anytime the point xy is on the graph, the point negative x, y is on the graph. Or for this example, if 3, 9 is on the graph, we have to make sure that negative 3, 9 is on the graph. So 3, 9 we know is on there. We have to make sure that negative 3, 9 is on there. Is it? So we can plug negative 3 in for x and 9 in for y, and it has to be true. All right, so if I plug the 9 in for the y, I'll have 9 equals, plug the negative 3 in for the x, negative 3 squared. Okay, so I have 9 equals, negative 3 squared is negative 3 times negative 3, that's 9, and that's true. So it works for that point. Let's try another example. Let's do 749. So we know that 749 is on the graph. In order, or if this graph is symmetric with respect to the y-axis, if 749 is on there, the point negative 749 has to be on the graph. Well, let's check and see if it is. So negative 7 is my x, 49 is my y. So I need to plug negative 7 in for x, 49 in for y, and see if it's true. So 49 equals negative 7 squared. 49, negative 7 squared is 49. That's true. So that point's on the graph. Okay, but if we want to prove that it's true, we have to prove that it works for every number, not just a few examples. And so what we have to do is put an arbitrary point, xy, on the graph. It's just any point in the world, any point that's on that graph. So if xy is on there, in order to prove this, we have to show that the point negative xy is also on the graph. Okay, so is it? So I should plug negative x in for x and y in for y and see if it's true. So I'm proving this now. So if negative x goes in for x and y goes in for y, I'll have y equals negative x squared. Y equals, and negative x squared is negative x times negative x, that's x squared. That's true. And that point has to be on the graph. Therefore, this is definitely symmetric with respect to the y-axis. All right, so here's another example. Y equals x to the third. We've graphed this one before, so you guys know what it looks like already. Let's consider a point that we know is on here. Here's the point 2, 8. And x is 2, y should be 8. Okay. So if it's symmetric with respect to the origin, if the point 2, 8 is on the graph, then the point -2, -8 has to be on the graph. Let's see if it is. Okay, so if I plug -2 in for x and -8 in for y, let's see what happens. That's not right. Let me try that again. The y should be -8 equals -2 to the third. And -2 goes for the x. All right, so what's -2 to the third? That's -2 times -2 times -2. That gives me -8. That's true, so that point's on the graph. Okay, again, we can't prove it like we want to do here with just a bunch of examples. All those examples can lead us to believe that it's true, but it doesn't really prove it. We have to prove it for every point. So let's just take any point on this graph, call it xy. Okay, so our goal then is to prove that -x, -y is on the graph. Okay, so I'm going to plug the x value here, the -x, in for x, and the -y in for the y. So I'll have -y equals -x to the third. So I've got -y equals, all right, -x to the third is -x times -x times -x, which is -x to the third. If I divide both sides of this by -1, I'll get y equals x to the third, which is what we started with. So that's true. All right, so some new terminology here. Remember, if a graph is symmetric with respect to the x-axis, then it's not a function. It'll fail the vertical line test. So we're going to talk about functions here. So the only two of our three kinds of symmetry that can involve functions are graphs symmetric with respect to the y-axis or to the origin. Okay, so an even function is symmetric with respect to the y-axis. An odd function is symmetric with respect to the origin. So even and odd functions are just other words for y-axis symmetry and origin symmetry. All right, here are two practice problems for you. Pause the video, work on these problems, and then we'll go over the solutions. All right, so let's have a look at number one. First of all, before we try to prove it, let's think of an actual example. So let's find a point that we know is on the graph of this function. So let's put a 2 in for x. If I put a 2 in for x, 2 to the fourth is 16. 2 times 2 times 2 times 2 is 16. All right, so I got 16 plus 3. That gives me 19. Right, in order for this to be an even function, it has to be symmetric with respect to the y-axis, which means that the point -2, 19, has to be on the graph. Let's make sure that it is. If I plug -2 in here, -2 to the fourth is positive 16. -2 times -2 times -2 times -2. 4 negatives will make a positive, so positive 16 plus 3 is 19, so that works. We have to make sure in order to prove it, though, that all points will work. All right, so to prove it, let's assume that the point xy is a point on the graph. So assume xy is on graph. We have to make sure then that negative x, y is on the graph. Okay. So let's do that. So let's plug negative x in for x. So if I put negative x in x's spot, I'll be finding f of negative x. It's negative x to the fourth plus 3. Negative x to the fourth is negative x times negative x times negative x times negative x, which will be x to the fourth plus 3. We get right back to where we started, so we know that that point is also on the graph. Okay. Let's look at an odd function. So let me make some room here. First of all, let's look at an example. So let's take, let's do a 2. There's not many things I can raise to the 5th power besides 2 in my head. So if I put a 2 in from x, 2 to the 5th is 32. Make sure of that. 2 to the 5th is 32, times another 2 would be 64. So point 2, 64 is on the graph. We have to make sure then that the point negative 2, negative 64 is on the graph. Let's check and see if it is. So if I plug negative 2 into this function, negative 2 to the 5th is, let's work it out. So if I plug in negative 2, I've got 2 times negative 2 to the 5th. Negative 2 to the 5th would be negative 32, times 2 would be negative 64. So that works. We've got it. Let's prove it now. Okay, so if the point xy is on the graph, we have to make sure that negative x, negative y is on the graph. So I'm going to plug negative x for x, and I'm going to plug, I'll put that in, so that'll be 2 times negative x to the 5th. Negative x to the 5th is negative x to the 5th times 2, so that'll be negative 2 x to the 5th. And so we have f of negative x is equal to negative, and notice that this right here, the 2x to the 5th, was what y originally was. So y is equal to 2x to the 5th, so it's equal to negative y, which means that the point negative x, negative y, has to be on the graph, and we proved it. All right, let me add a little clarity to the last problem that we did. So one clear way of knowing that a function is even is that if f, or is that f of negative x would equal f of x. This is what you already know. If I plug in, so another way of saying that is that if I plug in negative x for my x, then I should get the y value. F of x is the y value, so I get that. So if xy is on the graph, then negative x y has to be on the graph. Down here, if x, y is on the graph, and then I plug in negative x, I should get negative y. So when you're talking about function terminology, this is sometimes clearer when you're trying to prove if it's even or odd. Okay, here's one last practice problem for you. The function x to the third plus 7. So I want you guys to try to prove that that is not even, nor is it odd. It's neither one. Okay, so pause the video and try to do it, and use what I have highlighted here, these two definitions. All right, pause the video and give it a try. All right, so let's have a stab at this. So notice that on both of these, I need to plug in negative x. Okay, so let's do that. F of negative x is equal to negative x to the third plus 7. Okay. Negative x to the third is negative x times negative x times negative x. That's negative x to the third plus 7. We would like, in order for it to be even, we need to get f of x back out of it. F of x is x to the third plus 7. Well, this is negative x to the third plus 7, so it's definitely not that. So it's not even, because it's not equal to f of x like it should be. In order to be odd, it needs to equal negative f of x. What is negative f of x? So if I find negative f of x, I need to multiply both sides of this by negative. If I do that, I'm going to put that in here, I'll have negative f of x equals the whole side here has to be negative. So negative x to the third plus 7. But then I can distribute that negative sign, and I'll get negative x to the third minus 7. Well, that's not it either. And this is negative x to the third plus 7. So it's not odd either. So that function is not even or odd.